All right. We should be live. Let me know if there's any issues. Am I loud enough? Am I loud enough now? Getting any kind of echo. This is it. Now's your chance. Let me know. Otherwise, we're just going to barrel forward. Hey, everybody. Hope you're having a great Monday. I know I am. Have you been enjoying the interviews? I told you that we have a avalanche of interviews coming your way, and there is many more. I think the next one is the interview that I did with Dr. David Kipping from the Cool Worlds channel, and it's a long one. You know, like, we're such good friends, and so it went for about 90 minutes, and we talked about all kinds of stuff, and I think you'll really enjoy it. And then I just did an interview today about what's it going to take for a James Webb Deep Field survey, like the Hubble Deep Field. But and in the interview, the guy I was talking to, he was saying that they were able to accomplish in 50 minutes of James Webb time what took them 50 days of Hubble time. So how much better is James Webb over the Hubble Space Telescope? If it took you a day before, it takes you a minute now. It's bonkers. It's crazy. Okay, so if you're wondering what it is that you have stumbled into, you know. But this is my weekly question show. Your questions, my answers, you know the drill. Go ahead and put any questions that you have into the chat. And we've got two moderators here tonight, John Seffield and Zapfan, who will grab your questions and put them into this database that I can see, so that then I can start to answer your questions in rapid fire with no delay and no just extra chat, blah, blah. We just go straight into the questions. Boom, boom, boom for 2 hours. Now, we break this show up into two pieces. So the first hour is the one that I record, and this is the one that gets turned into the weekly question show. It gets trimmed down to about 40 minutes usually. And then, but there's a second hour. So remember, you were here for 2 hours, or I'm here for 2 hours. You're here for as long as you want. But that second hour we call overtime, and it is a lot more rapid fire. It is a lot more casual. A lot of back and forth. So, you know, depending on the style that you like, hopefully we'll be able to cover both of them. Now, I am going to jump in, and I've got a bunch of prepared questions, essentially the people who have put their questions into the comments, into the YouTube comments. And I want to give, some support to them first. So I'm going to answer their questions, and that'll give you time to get all of your questions organized so that we can proceed with the rest of the question show. But I have no idea what you're going to ask me. That's the fun part. So a couple of notes. One is I'm a journalist, not a scientist. So just keep in mind that if you're going to ask me a question that requires that I were a scientist to answer, I can't give you any information on that. I can help you understand what scientists think, but I can't go beyond that. So I will try to limit my answers to that kind of thing. And so if you're going to ask me a question that, scientists are arguing over, I can only tell you that there's an argument, not what is the right answer. I try to give emphasis to the people who have never had their question answered before. So if this is your first time here, I like your chances. So just keep that in mind. We know how many times we've answered your questions, that they've made it through to the actual show that we post on the YouTube channel. So hopefully we can spread the joy around. And then last, I sort of run a simulation in my mind of what are the questions that we tend to answer a lot. And so if I feel like, we've answered that question like 3 weeks in a row, I may skip it. Although sometimes I catch up during overtime. I sort of don't have a filter with overtime. I just hammer through the questions as quickly as I see them and don't even think about what the question is until I'm halfway answering it. So, okay. Yeah. So let's get into the questions. So electric master, there's a great example. Do you think that someone will ever solve the Riemann hypothesis? I don't know. How could I know? Not a mathematician. Not a mathemagician. All right. That's recording. That's recording. Here you go, Chad. These are my colors. At Tony Wells 6990. You can never prove that there is no other life in the universe. Oops. I didn't assign it. I didn't assign that. Okay. Better. Wait, what? Recording reminder. Yes, I'm recording. Okay. Now I'm allowed to do my show. Tony Wells 6990. You can never prove that there is no other life in the universe. Obviously, you've probably heard the saying that you can't prove a negative. So, you can't prove that we are alone in the universe. All you can do is search for life in the universe and fail to find evidence in a more comprehensive manner in a widening sphere around yourself. And if you assume that we don't live in a special part of the universe, that the amount of life that we find around Earth is roughly the amount of life that we will find in other parts of the universe, then as we explore farther and farther and we find no life, then we can sort of assume with increasing probability that the rest of the universe is empty. Or if we find one planet with life every 10 light years, then we can assume that that number will hold throughout the entire universe. Now, obviously, there are specific things like whether or not you're in the galactic habitable zone, whether or not your galaxy has lots of star formation in it, whether it had interactions with supermassive black holes. There will be modifications on it, but you can never know. There could be some little corner of the universe far, far away where life is hiding out, and totally, 100%. But, if we search for thousands of years and we never find one life form anywhere, and we've expanded, our civilization is now on 1,000 worlds and we've never seen anything ever, then at a certain point we can sort of safe to say we're alone in the universe. And there's like some practical work that's being done in this area. One example, and this was sort of originally for the LUVOIR telescope, the large ultraviolet infrared observatory, which was going to be the successor to the Hubble Space Telescope. And there was going to be a 8-meter flavor and a 15-meter flavor. And the 15, imagine a telescope that is 15 meters across. Like, it is to James Webb what James Webb is to Hubble. Like, James Webb is about 50 times more sensitive than the Hubble Space Telescope. And so LUVOIR would be about 50 times more sensitive than James Webb. And one of the things that it could potentially do is detect biosignatures in the atmospheres of other planets. Like, once astronomers finally stop arguing, they've decided what is the proper biosignature. And it could detect it in such a radius around us that you could rule out, like, if you don't see any life within the radius that LUVOIR could detect, then you could say with like 95% probability that we are alone in the universe. And then the next telescope comes out and maybe it has 50 times the resolution of LUVOIR, and then it would tell you that we are 98% likely to be alone in the universe. And so you'll never hit 100%, but if you're at like 98%, 99%, that seems pretty alone to me. Mantascatlaris 8261. Can scientists be full 100% sure if a certain asteroid will hit the Earth in the future, as they do in the movies, or is there always a small possibility that collision will just be a near miss? Astronomers tend not to work in certainties. And so when they detect an asteroid that has a orbit that will cross the Earth's orbit at the same time that the Earth is there, then they assign a probability. And in fact, astronomers have a scale that they use. It used to be called the Torino scale. Now I think it's called the Paloma scale. And with 10 on the scale being there is a 100% certainty that an asteroid is going to, or I think it's like, they never go to 100, I think it's like 90% certainty that there will be a large asteroid that's going to hit the Earth and cause damage at a global level. And then they scale that down where you can have a slight chance of a not very dangerous asteroid hitting us in the future. And so various asteroids will find their way onto the scale. And right now there are no asteroids on that scale. But at various times, asteroids like Apophis have gotten a slot on the scale, and then with more observations, astronomers are able to rule it out. And it's that needing more observations, right? It's that requirement that you pin down the location and the future movements of that asteroid with more and more certainty and accuracy. And the way it usually works out is an asteroid is found, astronomers do rough calculations, they realize that the asteroid has a chance to be kind of in the danger zone. And then they request time on other telescopes, more powerful telescopes. They do follow-on observations. They're able to trace and sort of specifically figure out what the future trajectory of that asteroid is. So we can never be 100% certain, but at a certain point, the zone of uncertainty for the asteroid encompasses the entire planet. And so at a certain point, a few years into the future, you will know that, yes, with certainty, that asteroid is going to hit the planet. And in fact, astronomers have gotten so good now that they are detecting asteroids on collision courses with Earth hours, days before the collision happens. They're able to know exactly when and where the asteroid is going to hit, and then people know to go out and watch for it. And so we recently just got one in Germany where astronomers predicted, actually, it's like one astronomer in Romania who is just crushing it. He's been finding all of these asteroids a few hours before they hit, and then all these other astronomers jump on their telescopes, they confirm the location and pin down. And so this whole prediction process is getting much, much better. With asteroids that are small, that are about to hit us in just a few hours or a few days, they're still working on being able to sort of push that back. And there are new telescopes and observatories that are coming online in the coming years that will do an incredible job of measuring as many asteroids as possible. So we don't know if an asteroid is going to hit us with a 100% chance, but at a certain point, the probability gets big enough that you start to say, should we send a DART-like mission to try and push it off its trajectory into something that's safer? But we do know with 100% certainty that asteroids are going to hit us. So when you think about the sizes of asteroids out there, like imagine like a 10-meter asteroid, the kind of thing that blew up over Tunguska in 1908. They can cause pretty significant damage on the ground. It blew down forests for thousands of square kilometers. Fortunately, nobody was there, but if it hit a city, it would be like a nuclear weapon dropping on a city. They hit us about once every 1,000 years. And that's like a 10-meter asteroid, something that is, that's a 100-meter asteroid. Smaller asteroids, like 10-meter asteroids, when you think about the one that exploded in the sky above Chelyabinsk in Russia, those happen about every 10 years. So we know that 10-meter asteroids, and generally they hit the ocean, like we don't even see them. But every 10 years or so, something explodes that is detectable. And then you've got the biggest ones, the 1,000-meter asteroids, kilometer across, and they can cause just wholesale destruction on a hemisphere of planet Earth. They're not as big as the one that killed the dinosaurs, but they're still a very bad day for a lot of people. And a few of those hit us every million years. And so if you run the clock for a million years, at the end of your million years, there will have been a couple of 1,000-meter asteroids that hit the Earth. If you run the clock for 1,000 meters, then you will have gotten one 100-meter asteroid. If you run the clock for 1,000 years, you'll have gotten one 100-meter asteroid, a city killer. And if you run the clock for 10 years, you will have ended up with one 10-meter asteroid. And it's just a probabilities out there. David Guy 209. Why is Jupiter so radioactive? Yeah, when NASA sends missions to Jupiter, one of the things that they need to keep in mind is the intense radioactive magnetosphere that is around Jupiter. That's not a great way to describe it. All right. When NASA sends spacecraft to Jupiter, they have to remember that there is this giant magnetosphere that surrounds the planet, and that is filled with particles that are high speed trapped from the sun. And they are just orbiting around Jupiter like a kind of a whirling, dangerous, radioactive buzzsaw. And we have that here on Earth. I mean, have you ever heard of the Van Allen belts? We have a magnetosphere around the Earth, and a portion of the magnetosphere is just holding these charged particles that are moving at intense speeds that were captured from the sun and space, and they're just whirling around the planet, following the magnetic fields of the Earth, like a giant particle accelerator that surrounds planet Earth. And there is one around Jupiter. Jupiter has a much larger magnetic field, and so is a much more powerful particle accelerator surrounding it. And so any time that a spacecraft needs to get close to Jupiter, it has to risk passing through this region of charged particles. And it encompasses the moons. So when you think about Io, Europa, Enceladus, when you think about Io, Europa, Ganymede, Callisto, they're within the magnetosphere. And so if you stood on the surface of, say, Europa, you would experience a lethal dose of radiation in like a day. It's that bad. And spacecraft, you want to send a lander to the surface of Europa, it's going to have to deal with all of that radiation. So you would expect any planet that has a magnetosphere also has like a dangerous charged particle environment around it that is lethal unless you zip in, zip out, or figure out some way to block the particles from causing damage. All right, so those were the prepared questions. So now I'm going to move in to your questions. Let me just find a good one to start with. So Richard Harris, I guess this is the kind of attention that you want to get, but has been commenting kind of conspiracy theory stuff on like every video that I make, and so has posted a bunch of questions. I think you love space, Richard. I think you love space. Like it's been going on for a couple of weeks now, and you're really into it. So like either you're curious about space and you're starting to wonder, are these conspiracy theories that you believe true or not? Or you just, I don't know, you find me magnetic? Maybe, but you enjoy the content. So thank you for contributing, for enjoying all the videos that I've been making, and keep it up. So Cosmos Web, you said, what exactly is a cosmic zoo? Are you talking about like the zoo hypothesis for the Fermi paradox, or are you talking about something else? So can you just let me know? Moon to Mars, what's your speculation with Starship 26? I can't speculate. I'm supposed to be a journalist. I'm not going to speculate. Can't make me do it. Okay, this is good. Connor Campbell, rogue planets are detected by their gravitational lensing when they pass in front of a distant star. Is there any detectable effect of gravitational lensing from exoplanets transiting their own star? Right. So this idea of gravitational microlensing, this is one of the lesser known techniques that astronomers use to find exoplanets. And what they do is they watch a large portion of the sky, watching a whole bunch of stars. And when an exoplanet is passing, or a rogue planet, but when a star with a planet or like a rogue planet is passing in front of another star, you can get this natural lens where the background object is lensed by the foreground object, and it distorts the light as it passes in front. And depending on the shape of the signal, like you can get, like if you get one star in front of a star and it's just a star, then all you get is this beautiful, perfect lens as they move in front of each other. But if there's like a planet orbiting around the star, then the lensing is like not a perfect sort of lens unlens. You get this sort of anomaly on the side of the lens. And astronomers can just measure how that light changes from the background star to determine what kind of a planet, the mass of the planet that is orbiting around the star. And one of the really interesting things about gravitational microlensing is this is one of the things that amateur astronomers can get involved in. So there is a sort of an alert network. And so if you have a small telescope and you have your own ability to measure the brightness of stars, you can watch as a star is passing in front. You can receive one of these alerts, and then they ask you to jump on and make observations of that star and then send in your brightness measurements. And then you can participate in discovering exoplanets. And it's done sort of piecemeal today, but there are a couple of telescopes that are coming out shortly. One is the Nancy Grace Roman telescope, which is going to be doing this really wide scale, huge field of view, and it's going to be watching and doing very deep images of the sky. But one of the things it will do, just like as a side benefit, because it's watching all of these stars, it will be able to detect all these little gravitational microlensing events. And it's thought that the Nancy Grace Roman telescope is going to find tens of thousands of exoplanets just through gravitational microlensing. And then the other one, of course, is Vera Rubin, which is the ground-based telescope that we're all so excited about. And same thing, it's going to be taking images of the night sky every couple of nights. It's going to be noticing for anything that is changing in brightness. And one of those things that could be a change in brightness could be, say, a transit or maybe even a gravitational microlensing event. The challenge with that is, you don't have a lot, it's not like it's continuous, and so you got to be able to do a follow-on observation. But it could very well be that it detects the presence of a planet as it's passing in front. Now, the question that you're asking specifically is that when we say do the transit method and we're looking, or the radial velocity method, and we're looking at a star and we're looking at a planet that is passing in front, does the, in addition to how the light of the planet is dimming the star, do you also get some kind of gravitational lensing effect? And my understanding is no. So I just wanted to talk about gravitational microlensing, but that was a cool question. Due to cost constraints, wouldn't it be cheaper to send multiple 10 to 100 plus satellites to deep space at a single time versus one at a time? We can get a lot more information and photos from more quick. Let me rewrite your question here. Due to the cost constraints, wouldn't it be cheaper to send multiple satellites to deep space at a single time versus one at a time? So this happens all the time. There is a thing called ride sharing where you'll get, say, a space. There are situations where you will have a rocket that is carrying some flagship mission. Maybe it's a big communication satellite or a weather satellite or something like that. But it is also carrying a whole bunch of smaller satellites on board as well. And then it will, like, as long as the smaller satellites are okay with the same trajectory as the larger satellite. If you just want to be in low Earth orbit, or you want to go to the, some Lagrange point or something like that, then you can ride share along. And often you'll have this big satellite, and then packed around it are lots of little CubeSats. Also, SpaceX from time to time will actually do ride shares where they will encourage, people with smaller missions. They'll gather them all together, and then they'll launch, say, 50 spacecraft at the same time. Again, same constraint. You need to be okay with going to the place where the rocket is going. So if you've got some custom, like if you want to be on a polar orbit while everybody else wants to be on an equatorial orbit, then that you're not going to want to be on the rideshare. And you may have to pay for the custom rocket lab. You may have to pay for the custom rocket lab launch to be able to go to the specific orbit that you want. Once you're starting to go beyond Earth orbit, though, then you run into constraints of transmission, of communication, because you're going to have to communicate far away from your spacecraft. And that often requires a larger spacecraft, something with more power, something that can generate hundreds of watts, something with a larger transmission dish that can actually be able to communicate out to, all the way from the asteroid belt back to Earth. And so that tends to require a bigger spacecraft. And then also, like the kinds of scientific payloads that you're going to want to do. Like if you're going to want a mass spectrometer, if you're going to want a laser altimeter, if you're going to want a ground penetrating radar on your spacecraft, then you're going to need to have more power. And so more power means a bigger spacecraft. And so, you're going to need a much bigger spacecraft. But there really is a revolution in miniaturization of spacecraft that has started within the last couple of decades. And we are well on our way into this new generation where you can miniaturize the propulsion system, you can miniaturize the communication system, the optics, the computers. I mean, think how small cell phone cameras are today. You can put those on spacecraft now. And so you have CubeSats, which are kind of like the size of a bread box, but there's ones that are a segment of a CubeSat, things that are like that are as big as a paperback book. And so you can imagine future satellites that are even smaller. And there are new technologies that may move away from some of these other ideas. One, for example, is being able to send your spacecraft in swarms. So instead of sending one spacecraft to do the job, why not send 100? And the 100 will communicate together and be able to work like one big spacecraft. And if there's a problem in any one of them, it doesn't really matter because they can all communicate and take over from one another. There are also other ideas where, like, say you want to communicate your data back to Earth. So what you do is you send, say, 100 spacecraft to different asteroids, and they fly out into space. They take a whole bunch of images of the asteroid that they've been tasked with, and then they fly back on their orbit, and then they transmit all their data when they get back to Earth. You don't have to worry about a big transmitter. Wait until your satellite has returned. Now, it's going to take you a couple of years. You have to be patient, and you don't know if your spacecraft's okay, but it can be that you might be able to do that. And also with the Perseverance rover, NASA tested out this idea of, can we use smaller spacecraft as transmitters? So with Perseverance, they also sent 2 CubeSat scale spacecraft to Mars. And they were the ones that were doing the transmitting back home, not Perseverance. Perseverance was testing out, can I relay my communications through these CubeSats to be able to send this data back to Earth? And the test worked out really well. So we're sort of in this middle zone where, like, we can see that these big flagship missions, it's a really hard thing to justify spending $5 billion on this gigantic spacecraft. Is there a way to miniaturize the capability? Are there ways that we can use interesting orbits, new technology to be able to still get the science done, but be able to do it on a much lower budget? And the answer just keeps turning out to be more and more yes. Bug bite. What is your personal opinion on the shape topology of the universe, observable or otherwise? As I say all the time, I'm not a scientist, I'm a journalist, so I don't have opinions about this kind of thing. But scientists think that there are different kinds of topology for the universe. Topology is like the shape, right? What is the topology of a sphere? Think about a topology of a donut. These are different sort of shapes of objects. And so there's kind of 2 possibilities about the universe. One possibility for the universe is that it is infinite, that it goes on forever. And it is really hard then to describe what is the shape of something that goes on forever. It goes on forever in all directions. And so, it's kind of hard to have a topological discussion about that. But the other possibility is that the universe is finite, that it doesn't go on forever, that it wraps in some way. And you can sort of imagine a 3D game of asteroids where you go to the side of the screen and you pop out from the other side of the screen. You go to the top of the screen, you pop out from the bottom of the screen. And then what you can't do in asteroids, you go out the front of the screen and you return in the back of the screen. And for the universe to be finite, then one of those questions that astronomers ask is, what is the topology? What is the shape of this finite universe? And can we get a sense of what it is? And so one of the questions that astronomers have asked is, can we measure the flatness of the universe? They think about like the largest possible triangles that you can imagine and make sure that the angles of the triangle add up to 180 degrees. And they find that they do, that the universe is flat. And so when you think about the possible topologies, like the universe could be a sphere, but a sphere wouldn't give you triangles that add up to 180 degrees. When you think about sort of putting a triangle at the equator of the Earth, you can have them go up to the North Pole, and the angles don't add up to 180 degrees. Or you could have something where the angle is less than 180 degrees, some kind of like, is it saddle shaped? But from what they can tell, the universe is flat. And so then you've got to think about possible topologies for a finite universe that could be flat. And so I'll give you a couple of examples. Like one is a cube, right? Like if you want to travel in, if you say you send two lines, parallel lines, and they stay parallel forever, and they go along one side of a cube, and then they go over the corner of the cube, and then they stay parallel, and they keep going no matter what direction you send those lines, they're going to remain parallel. And then the best example is a torus, a donut, where if you think about a donut, same thing. You start parallel lines anywhere on a donut, and they will remain parallel. You can go around the top of the donut. You can go around the edge of the donut. And that's the one, like there are other shapes, dodecahedrons, 100-sided geometric things, and all kinds of other possibilities. But I like donuts the best. So in my personal opinion, the universe is a donut, but that is not based by evidence. That is just based by hunger. Donuts. ASCII, what happened to the periodic methane emissions recorded by, if I recall, the Mars orbiter some time ago? So what you're referring to was periodic methane emissions that were detected by the Curiosity rover. And noticed every springtime, the methane around the rover spiked. And that led astronomers to wonder what's going on. Here on Earth, atmospheric methane is driven by a biological process. Bacteria, cows. But also, we know that some amount of methane in the atmosphere can be driven by non-biotic process, volcanoes. And so the question is, which is it? And with the discovery of this atmospheric methane that appeared in the springtime when things were warming up on Mars, that feels really like an indication that there is, like, life is starting to use this methane. And so astronomers have and so NASA has sent other missions to Mars, ones that have gone and actually been able to map the atmosphere of Mars. And they're still not entirely sure what the source is, but there was a paper that came out just a couple of weeks ago. Like, I haven't heard a lot on this for a while. And then just a couple of weeks ago, we got a paper that said one possible explanation is that in the springtime, as Mars warms up, it puffs out the atmosphere a bit as it's interacting with the sun. And what that can tend to do then is draw out volcanic gases from reservoirs under the ground. So if you imagine, like, underneath the ground on Mars, you've got all of these volcanic chambers that are all connected together, and they're in a state of equilibrium with the overall atmospheric pressure. But as the region heats up, the atmosphere warms up, atmosphere kind of puffs out a bit, and it draws atmosphere out of the ground, which has been inundated with these volcanic gases, methane. And so that's a perfectly non-biological explanation for the discovery of methane at Mars. So I hope you're keeping track of this, right? That every time we think we've found life on Mars, it turns out that the results are inconclusive. The Viking experiment, the Allen Hills meteorite, methane on Mars, phosphine on Venus. Like, it just goes on and on and on. And I always say, be patient, buckle up. This mystery is going to take a while to resolve. David, hey Fraser, do you think that a major step in improving propulsion speed? David, hey Fraser, do you think that a major step in improving propulsion speed so that travel time to the outer solar system and beyond will be achieved in our lifetime? So I think there are a lot of improvements in propulsion that have already been developed that just need to be implemented. Traditionally, right, the fastest method of propulsion that we know of is a chemical rocket. or I mean, it's not the fastest that we know of, but it's the one that gets used. Now, ion engines have been used, and they can achieve much higher speeds, but you can't do a lot of thrust. But as long as the ion engine can be turned on for days, weeks, months, years, it can reach enormous velocities with very efficient fuel use. And so what comes next? There's an improved version of an ion engine called a Hall effect thruster, and it's been proposed that you can attach a Hall effect thruster to, say, a fission reactor. So you generate electricity with a fission reactor. You are using that to propel ions out the back of the spacecraft, and you can achieve very high velocities. I mean, you should be able to achieve delta Vs in the tens of kilometers, maybe even 100 plus kilometer per second, which gets you out to the outer solar system within, a decade. There are proposals for fission drives, which it's expected that NASA is going to test a fission-based rocket probably in the next couple of years. They're great for transportation in between planets in the inner solar system. Like if you want to do a mission to Mars, you only want to take 90 days to get there. Then you use a fission rocket. And then there are a lot more exotic ideas. There are solar sails that you do a maneuver, the Oberth maneuver, where you drop into the inner solar system, go past the sun, use the intense power of the sun to accelerate your solar sail, and that gets you out to high velocities out into the outer solar system. There are light sails, laser sails, where you fire a high-powered laser at a small probe with a solar sail, and you're able to accelerate it to, theoretically relativistic velocities, but even thousands of kilometers per second would be terrific. There are electric sails and magnetic sails, which interact with the solar wind coming from the sun, which theoretically can drive you up to 100 plus kilometers per second. So there are a lot of really interesting ideas that are just around the corner. And then there are the tried and true technologies that NASA and ESA and all of them have been depending on for literally decades. And it requires an investment. It requires someone to say, let's try and remove some of the risk from this technology and find out if we can make it work and be willing to invest money in it. Generally, people go for things that are tried and true as opposed to experimental technology. But every now and then, for the purpose of a mission or for the willingness to understand if we can make better technology, these really cool new propulsion systems fly. And I think that's what we're going to look at for the next, when you say in our lifetime, like those are the kinds of technologies that will probably be explored in our lifetime. And then the ones that will come after our lifetime are probably things like fusion drives, which will they won't get you necessarily to the nearest star, but they'll definitely give you a lot of speed here in the solar system. And then antimatter is the ultimate propulsion system, because it is the most energy dense source that you have. It's just very expensive to make antimatter at the amount that you would require to be able to travel interstellar distances. So we are, decades away from exploring some of these other technologies at scale. And then we are centuries away from the really advanced technologies, which, sucks. I'd love to see the first antimatter spacecraft set off to another star system, but I get to see pictures from the surface of planets in the solar system, and that's okay. Ernest Patriot. We can thank the gravitational effect of having Jupiter nearby, where that mass has altered the flight path of potentially deadly encounters with asteroids. People say that Jupiter is like our protector, and sure, Jupiter's got a lot of mass. It gobbles up a lot of asteroids that would have stuck around inside the solar system. But Jupiter is a bully, and it causes as much harm to Earth with its gravity as it protects us. So when you think about Jupiter and its interactions with the asteroid belt, every time Jupiter orbits around the asteroid belt, it causes these perturbations in the belt, and it kicks asteroids from the asteroid belt into orbits that bring them closer and closer to the inner solar system. And all of the near-Earth asteroids that have the potential to cause great damage on Earth are all being driven by Jupiter's gravity. Jupiter is just pushing these asteroids into the inner solar system all the time, and they are shifting and changing, and they're interacting with Jupiter more, and they're constantly ending up closer and closer, and then eventually they crash into Earth. That's what clears them up, or Earth's gravitational interaction kicks them back out again. But no, Jupiter is just like, why do you keep hitting yourself? Why do you keep hitting yourself? Because it's just constantly throwing all those asteroids. And in fact, this is one of the reasons why astronomers can't make really long-term predictions about the movements of asteroids, is because Jupiter is constantly pushing these asteroids around. It's like a train of asteroids that Jupiter is responsible for. So no, Jupiter is not your friend. Like Jupiter is at best a frenemy. Stephen Nard, please tell me if a black hole is two-dimensional or spherical. Well, so when you sort of see the pictures, the illustrations of what a black hole looks like, you see this sort of fabric of space-time, and then there is this well, and down at the bottom is the black hole, and that's a way to sort of wrap your mind around how black holes are distorting space-time. But that is like a two-dimensional representation of an effect that's happening in three dimensions. The reality is that you would need to sort of recreate that weird model in all directions and in all dimensions. A black hole is a three-dimensional object. Think of a neutron star, which is the result of a very large star that explodes as a supernova, and then the infalling material collapses down, and you end up with this rapidly rotating object that is incredibly dense and has these magnetic fields and so on. And the only thing that is stopping the neutron star from collapsing down is the pressure, the neutron pressure that stops these neutrons from being smushed into each other. But you could take the sun, or maybe, you could take the sun and you could replace it with a neutron star with the mass of the sun, which you don't get. I mean, they're generally a little bit more massive than that, but you could, if you could. And the sun would just continue to orbit. All of the planets would continue to orbit around this neutron star sun, and everything would be just fine. And so if you think that a star is a three-dimensional object, a neutron star is a three-dimensional object. But if you feed a neutron star like one more bite that's wafer thin, one more straw to break its back, then it overcomes the pressure. The neutrons are now, they give up. They're willing to be squished together, and this thing compacts down into one more size, and that is the black hole. And now suddenly the event horizon forms around the black hole, because that is the region where now not even light can escape this thing. And so it is still a three-dimensional object. You can orbit a black hole in any orientation in exactly the same way. So black holes, they are spherical. But like, spherical is not exactly the right answer, because they rotate. They're oblate spheroids, but they are three-dimensional objects. Okay. Intern, what is the most important resource other than water to find on the moon for a permanent human settlement on the moon? I can tell you what the next three most important things are to find on the moon. In fact, they're more important than water, and they are power, power, and power. Energy, energy, energy. Those are the most important things to find on the moon, and they are really the limiting factor for being able to have some kind of science settlement on the moon, some kind of science station on the moon. When you think about the moon goes through this 28-day cycle where half of it, 14 days, it's in permanent sunlight. Half of it is in permanent shadow. And so you've got to spend this time where the temperature ranges between plus 150 to negative 150 or more. and it just swings back and forth. And so when you're in full sunlight, you need really good air conditioning, which is fine because you've got all that sunlight, you got all that power, that's no problem. But then when you go into the cold part, then you need a way to warm up your station so that people don't freeze. Now you can dig underground and whatever, but you're going to need, for communication and your science equipment and all of your rovers and all this kind of stuff, you're going to need a ton of energy. And that's really going to be the limiter. How much regolith can you turn into buildings? How much water can you electrolyze to be able to separate into oxygen and hydrogen? It all takes electricity. It's all going to take power. And this is one of the technologies that NASA has been investing in pretty heavily recently, which is some kind of moon-based fission reactor. And in fact, they're just in the process of going through the shortlisting. They're just in the process of going through shortlisting different ideas for fission reactors that can be used on the surface of the moon. The kinds of things that could provide, say, 1,000 to 10,000 watts of energy for 50 years, that they could send one of these things up there, they could hook it up to the station, they've got as much electricity as they need to get them through the lunar day and the lunar night and just keep going. So really that's it. It's all, once you've got electricity, once you've got power, then you can kind of do everything else that you need. But without power, you can't do anything. Carl Smith, if you had $1 for every Rouge planet misspelling, how rich would you be? Good point. But like, haven't we all got that when we play Dungeons and Dragons? And people write on their character that they're a Rouge. Ted Cruz says, Elon Musk said anything about leaving SpaceX? No. Has he? I don't know. Have you heard that? Misa Likeu, is Europa Clipper really happening? Absolutely. It's soon, like it's launching in 2025. Like we are a year away from Europa Clipper launching. It is almost complete. Thomas O'Neill, what is the speed of love? So is it pheromone based? Is it like when you see a person that you love, then that's the speed of photons? I'm just going to say it's the speed of causality. That seems like the easy answer, is that the speed of love is the speed of causality. If you feel the earth move, speed of gravity. Sorry, just looking for another question. What do we got? We've got about 12 minutes left for the main show, and then we'll switch over to overtime. Sorry, just looking for a question. There's some questions here that I kind of don't know the answer to, but I really like the question. Okay. Kevin Kernick. Hey, Fraser, how do gravitational wave detectors determine where the wave event came from? I'm understanding how they make the detection of the event, but how they determine where it originated. So when you think about the various gravitational wave detectors, we'll take LIGO for starters, that it is this facility with these long arms. They are a kilometer long, 10 kilometers long, 10 kilometers long. And they run this laser down the arm and it bounces back and forth to form kind of like a virtual arm that is vastly longer. And so when a gravitational wave passes over the gravitational wave detector, then it changes the length of one of the arms, but not the other arm, or it changes the length of one arm more than the other, sort of depending on the angle that the gravitational wave comes through. And that makes a detection at the gravitational wave facility. But that could just be a little earthquake. It could be a truck driving past. It could be somebody setting down their coffee too hard when they're in the office. Like, these things are really, really sensitive. So they have a second facility. There's one in Eastern Washington. There's one in Louisiana. And the one in Louisiana and the one in Washington, they both have to detect the event. And so you get the wave passing one facility, and then a fraction of a second later, the wave passes the other facility. It has to have the same wavelength, has to sort of have the same properties, and that's how they know, that's how they detect and confirm that there was a gravitational wave. But when you only had the first two LIGO facilities, you had a really hard time knowing where in the sky this event was happening. So you could, like, if the wave passed one detector then the other, then it came from over there. But if the wave passed this one, then that one, then it came from over there. And so you pretty much could only narrow it down to one hemisphere of the sky. But we got a third detector with the Virgo facility in Europe. And so now you've got this equilateral triangle around the Earth. Two facilities in the US, one in Europe. And so no matter what direction the gravitational waves are coming from, you're able to determine the location in 3 dimensions in the universe and to be able to track it back. And so from this point on now, astronomers know to within a couple of degrees of the sky where the gravitational wave signal came from. And there are more gravitational wave facilities coming online. You've got the Kagra facility. There's a couple more planned. I know the Chinese are planning gravitational wave observatories. And so each one of these new observatories, as it comes online, will be able to add to the sensitivity and the location finding and the confirmation of these gravitational waves. And we talked about, I think last week, about how the European Space Agency has approved the LISA mission, which is going to be 3 gravitational wave observatories that are going to be in space. So now you've got another set of facilities that could potentially detect gravitational waves that are the same as the kind of ones that could detect on Earth, and you get more sensitivity. So it's like this growing network. The more detectors you put on Earth, the more value you get out of them. Terry Davis, is there a plan to look at stars that resemble ours with planets not tidally locked? I mean, the holy grail of exoplanet hunting is to find an Earth-sized world orbiting around a sun-like star in the habitable zone. But the problem is that for us to be able to detect the presence of that planet, you're going to need a very powerful telescope that is able to block the light from the star to be able to look at the planets themselves. So far, like just using, say, the transit method, astronomers have not found any planets that are like the Earth and the Sun. And when you look at the kinds of planets that they have found, that tells you sort of what the problem is. So what they found is Earth-sized worlds orbiting in the habitable zone of red dwarf stars. And in this case, because it's in the habitable zone, it is much closer to the star and it's orbiting a lot more quickly. It might take only a couple of weeks to go around the star. And so you get confirmation, confirmation, confirmation. And so you know that your planet is there. They've detected hot Jupiters that, again, you've got a planet that is going around its star. It could be a sun-like star and the planet is only taking 3 days to go around its star. And so you get confirmation, confirmation, confirmation. But when you think about what's going to happen for us to be able to detect Earth, you need to be watching a sun-like star. You need to watch as an Earth-like planet passes in front of it. You have to know to watch again in 365 days, or just like not look at anything else, just watch that one star, wait for that planet to come back. 360, but you don't know how long it's going to take. It could take 1,000 days. It could take 7 days. You don't know. And then you have to wait another 365 days to get another confirmation as it passes in front of the star. So like the bare minimum, you need 2 years of continuous observations. And the Kepler spacecraft, which unfortunately died, this was the plan, was they took this spacecraft, they were going to stare at this gigantic field of the sky for months at a time. And the hope was that it would be able to detect that very rare transit of an Earth-sized world orbiting around a sun-like star. But unfortunately, the reaction wheels on the Kepler mission failed, and so it wasn't able to hold its position. And so they had to come up with a different strategy. They used it for looking at red dwarfs. They weren't able to use sort of its full, complete plan. And there hasn't been a replacement. There's TESS, but TESS isn't exactly up to this. So right now, there are no missions in the works to try to detect, to kind of to redo what Kepler was going to try to do. And I think that's a problem. I think, and I'm sure the astronomical community is aware of it, they've got a plan for this, but I've interviewed tons and tons of people, and I haven't found anyone that's given me a really satisfactory answer. Like, what is Kepler died. It didn't do its primary mission. It wasn't able to find that Earth-sized world orbiting around a sun-like star. People are planning the Habitable Worlds Observatory, which is going to be this telescope capable of observing an Earth-sized world orbiting around a sun-like star. But there isn't a lot of space satellites that are in the pipeline to do the finding, to find all of the candidate exoplanets first, so that then you can actually know to do your follow-on observations. Now, there's a telescope that I really like called LIFE, and it sort of has two modes. One is, it's an interferometer, which, I love. And one possible version of it is that you would be observing individual exoplanets and try to, orbiting around sun-like stars and try to look at the planets. But if you don't have candidates, then you can look at lots of other planets and try to identify new candidates. And so I think if there's like one telescope that I would love to see move forward, like if I had to choose between the Habitable Worlds Observatory and LIFE, I would probably choose LIFE. It's an interferometer. It uses nulling to provide its coronagraph. I've done an interview with the principal investigator on it, and I think that's the space telescope that I'm most excited about. So no, there isn't a great plan right now to be able to see those Earth-sized worlds. There's like, let's make the powerful telescope that can observe them in the 2040s. And there's like, let's use TESS to find all of the nearby exoplanets. But there's in the middle, this sort of question mark, when we need to find thousands of candidate Earth analogs that then can be observed by the Habitable Worlds Observatory. And right now that just doesn't exist. We have not found one single Earth-sized world orbiting a sun-like star in the habitable zone. We have not found Earth 2.0 yet. Always choose life. Okay, let's move on to the overtime. But before we do that, I've got to do all of my administration stuff. So this is your chance to go to the bathroom, to grab a snack. I've got about 5 minutes that I've got to do, and then I'll wrap through that really quickly, and then we'll switch over into overtime, and we'll stick around for another hour. So we're halfway there. Can you prove there is no life in the universe? Could we know if an asteroid is going to hit us? And why is Jupiter so radioactive? All right. Can you prove that there's no life in the universe? Can we be sure that an asteroid is going to hit us in the future? And why is Jupiter so radioactive? All this and more in this week's question show. Welcome to the question show. Your questions, my answers. As always, wherever you are, across my channel, if a question pops in your brain, just write it down. I will gather them up and I will answer them here. All right, let's get into the questions. Now, you probably noticed the Star Trek planet name that's appeared above my shoulder. If you haven't, they'll be back. Don't worry. And this is a way for you to vote, for you to tell us what you thought was the best question of the week. And so when we added up all the votes from last week, the answer we got was from Noor Ahmed. How has information about space research become more truthful or more muddied than it was in the past? And I guess that gave me a chance to talk about what I'm specialized in, which is space science communication, which was a lot of fun. So thanks for the question. Thanks everybody who voted. So remember, you're going to see the planet names come up at the end of the episode. Write down the planet that you think was the best question, best answer. We'll tally them up and we'll celebrate it next week. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that are in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to the recent newcomers. Lee End, Exist Dissolve, Douglas Friday, Ryan, Alex Ratout, Russell Spivey, Robin A. McIntyre, Silent Phoenix, Yves Junkera, Jacob Howell, Mark Johnson, and Brian Mendoza. Join the club at patreon.com/universe today. All right, those are all the questions that we had this week. Thank everyone for asking the questions in the YouTube comments. And thank you to everybody who joined us for the live show. Now, we do the show every Monday at 5 p.m. Pacific time. So if you want to join in the show, it is like twice as long as the episode that you're watching right now, with questions, follow-on questions, overtime. It's a lot of fun. Monday, 5 p.m. I'll put an event here on the channel for the next one, and you can figure out a way to remind yourself to join that show. All right, we'll see you next week. I'm going to talk about smaller, good space YouTube channels in a second. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Antonio Lofilara, David Giltonen, Dougie Stewart, Dustin Cable, George, Jeremy Mattern, Jordan Young, Josh Schultz, Mark Anstis, Paul Rohrbach, Stephen Krasaki, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other patrons. All your support means the universe to us. So in the last question show, I got a question from someone which was like, who, with all of the low grade spam content here on YouTube, that it's hard to know what is real and what is not, and who can you trust and who can't you trust, people wanted some of my recommendations. And I went through all of the big heavy hitters who you're all very familiar with. Many show up on my channel all the time. And it sort of made me think, like, there's so many great smaller creators, people who are in the under 10,000 subscribers on YouTube, who are doing an amazing job of communicating, and they're just not getting enough support. And I want to try and use my channel to be able to drive as much support for these other channels as I can. And so I know a bunch of these channels, and I will recommend a bunch at you in the coming weeks, but I would love for you to tell me, like, what are some channels that I should go and take a look at? Put them in the comments down below. I will go and check out their channels, and if they meet my criteria of like science, if they're saying good things, they're saying proper science, I will sort of gather a bunch of those up, and I will try to highlight a few each week for the next I don't know, for as long as it takes for me to run out of channels, which might be forever. I don't know. So, but I want to sort of start this ball rolling, and that is, I did an interview about a week ago with Dakota Tyler, who is a postdoc. He's a doctoral student at the University of California, Los Angeles. And he was the researcher who's working on this planet with a comet-like tail. And he had been on the weekly Space Hangout for a couple of weeks as well before we shut that down. But I didn't realize that Dakota's got his own YouTube channel, and he's got his own TikTok, and he's got his own Twitter, and he does a ton of really interesting videos sort of from his perspective as an exoplanetary scientist, but also with, some of the more other topics that he looks into. And so I wanted to point you towards his channel this week, which I sort of didn't realize how active he was across all the social medias. So that's Dakota Tyler. His sort of handle is Star Kid, which I think is awesome. So definitely check out his channel, and then give me recommendations for channels of other people here on YouTube or even across other social media who don't have big followings, who you think are underrated, who could get more fans so we can help get more positive voices in space science. All right, we'll see you next week. All right, save that. And then I will save my audio, and then we'll move into overtime. Okay. So before we go into overtime, so Richard, I know that you are the lone conspiracy theorist here in the chat, and or you are a skeptic of like all things space, but like it's not really positive engagement if you're just going to come in here and um, I don't know, bomb a bunch of stuff that you've been thinking about space. Like if you have genuine questions, then ask them. But I think you're just trying to cause arguments, and so I'm going to gently encourage you not to do that. You say you respect me. If you respect me, just go along with the flow, man. So that's your warning. Your kind Canadian polite warning. Hello, patrons. Welcome to the overtime for QA episode 247, recorded on February 5th, 2024. Here we go. All right. Cosmos Web. How can black holes have infinite mass and not tear a hole in the fabric of space-time? Well, like, how do you tear? Like, how do we know? Like, just because people call it fabric sort of makes you think that you could tear it. And, we don't know what it would take to tear, if it's even possible. So, yeah, black holes are crazy. They don't have infinite mass. They have infinite density, but they have a finite mass. And so we don't know what that does to space-time. We know it tangles it up into little knots and causes it to torque around with all kinds of relativistic effects, frame dragging and all that, which is already mind-bending enough. But we don't know, like, what would it even mean to tear the fabric? Like, can you repair it again? Can you sew up space-time once you've torn it? What kind of a needle do you need to do that? Misaliq, where are we with the upcoming Venus missions? We're exactly where we were, which is that there are 2 NASA missions that are in the works for Venus, and there's 1 private mission that is planning to go to Venus. There's some concern that one of the NASA missions will have its schedule slip with sort of because of other missions that have slipped. But if all goes well, we should see multiple missions to Venus heading out towards the end of the decade. Noor Ahmed, hey Fraser, since I read the article about space debris on Universe Today, I've been wondering, are there any companies or researchers being prioritized for space debris clearing? Cleaning space debris is a tricky problem because, as I mentioned in the last question show, or maybe it's the question that's coming out tomorrow, there are potentially millions of pieces of space debris that are, each one is its own special butterfly. And so if you wanted to grab a piece of space debris, you would need to launch a rocket, which is going to generate space debris. There's no way around this. So the only practical idea is lasers. And there's a bunch of people that are thinking about this. You fire a laser at a piece of space debris. It causes a little vaporized segment on the space debris, which acts like a little thruster. And so you have this laser sitting there and it just goes zip, 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 and just hits a whole bunch of pieces of space debris. And then each one gets a tiny little thrust against its orbit direction that causes them all to lower down. And there was a proposal that just came out this week about this. I've been tracking a whole bunch of them. And I think that's going to be the solution, either a ground-based or a space-based laser array that is around the Earth that is trying to deorbit as much of this debris as possible. But you can imagine what is space debris and what is an enemy satellite? You can imagine someone firing this high-powered laser at an enemy satellite. You're going to blind the sensors on it. You're going to potentially, you could deorbit a satellite. You can melt parts of it. Like these are going to have to be very powerful lasers. At the same time, powerful lasers in orbit could be used to accelerate spacecraft to Alpha Centauri. And so there's like lots of really good reasons, but people can't get along sometimes. And so I think it's going to be a pretty hard sell for people to go, yeah, go ahead and put a high power laser in orbit. But then we already have nuclear weapons. Like we already have ways to wipe each other out at scale. So, what are you going to do? Trey Harmon, is dark matter hiding in our Lagrange points? So it all depends on what dark matter is, but dark matter is affected by gravity. And so when you think about not the L1, L2, L3, but the L4 and L5, which are these gravitational valleys. Yeah. You can imagine dark matter falling into these, interacting in 3-body interactions with various asteroids, and they could get trapped in the Lagrange points. But it depends on what they are. If they are slow-moving particles, and there's lots of them in the solar system, then you could imagine that would happen. But if dark matter is actually primordial black holes with 1,000 times the mass of the sun, no, there are no 1,000 solar mass black holes hiding in the Lagrange points. So, we still just don't know what dark matter is. There are ideas that that if there's dark matter that's trapped inside gravitational wells, say there's dark matter inside the sun or there's dark matter inside Jupiter, then because it's trapped, it's going to self-annihilate. It's going to crash into each other. It's going to annihilate. That will cause a little extra heat on the sun or on Jupiter, and that would be detectable, that you could actually detect the presence of this additional heat that would be more than what you would expect if you just made observations of Jupiter. So that might be a way to detect if dark matter is a particle and it's hiding in the solar system. And so same thing, you could imagine like an excess of heat inside coming from the Lagrange point, maybe Jupiter's Trojan points, and you'd be like, okay, maybe that's coming from dark matter. The asteroids in the Trojan belt are like a little warmer than they should be. That's not a terrible idea, actually. I'll pass that along to the researcher. There's one researcher who is really focusing on this. If there's dark matter inside things, then we should be able to detect the heat. I've interviewed her in the past, and I'll pass your idea along to her, and she'll probably like it. David Swenson, would the L4, L5 Lagrange points be, these Lagrange questions, how great is this? Would they be potential locations to search for interstellar probes observing the Earth? I mean, not just searching for interstellar probes that are observing the Earth. It would be the place to search for interstellar probes that have long since died when they were once observing the Earth. That these are traps that grab stuff and they hold on to them. When you think about the Trojan belt at Jupiter, they contain tens of thousands, hundreds of thousands of objects. There's as many objects in the Trojan belts around Jupiter as there are asteroids in the asteroid belt. Like there's a lot of stuff in there, and they are trapped. And it is a relatively small area that you could search. And so, yeah, like if someone said, I want you to search the solar system for some evidence that some extraterrestrial intelligence has been visiting the solar system at any time in the past, I would beeline it for the Earth's L4, L5 Lagrange points. And I would put some kind of spacecraft up there that is looking for an ancient von Neumann probe factory in the L4, L5 point. It is the obvious place to put some kind of facility is the L4. Like, is this a science fiction story? I think it is. 3M. Any updates on the Titan Dragonfly mission? No updates. No good updates. No bad updates. Like everything is just moving according to plan. I think it's launch in 2028 and arrival like 2030 forever. I don't know. No, wait, 2027. Like we're just a couple of years for the launch of the Titan Dragonfly. It's just going to take a long time to get out to Saturn. Ken Hargraves, what is the latest news on sending craft to those interesting moons that could have water? Well, the spacecraft that's going shortly is the Europa Clipper, and it's going to be going to Europa, and it's going to be launching, I think, 2025. So we're just a year and a half away from Europa Clipper launching, and it's going to take a couple of years to get out to Jupiter, and then it's going to be studying Europa. The European Space Agency's JUICE mission has already taken off. It's going to take its own time to get out there, but by the late 2020s, early 2030s, we're going to have 2 spacecraft examining the moons of Jupiter to try and understand the presence of water underneath the surface. Bonsai fan, what do you make of that galaxy ring found by a British student? So I think you're talking about there's these 2 rings in the sky that were gigantic, like billions of light years across. And I don't have an opinion, but the opinion that astronomers have is one possibility is that this is evidence of baryonic acoustic oscillations, which are essentially frozen sound waves that were passing around in the early universe shortly after the Big Bang, that then they turned into patterns in the cosmic microwave background radiation, and then they turned into overdensities in the universe, places where galaxies would come together, and then you get these giant sound waves in the sky. And it's such an amazing idea. Another possibility is it's cosmic strings, and then there's even more exotic possibilities, like it's evidence of a cyclical universe, that this is some kind of echo from the former universe that somehow made it through to this universe. I gave you that in the order of what people think. Frustral Niece. After the not so successful missions to the moon, why are we more successful in landing on Mars? Seems like those missions have been far more successful. Well, for the longest time, there was this idea that it was impossible to land on Mars, that Mars eats spacecraft for breakfast. And they call it the, oh my God, what do they call it? They call it the Martian gremlin? No, something like that. Someone in the chat is going to get it for me. So thank you in advance. And when you say it, there's some kind of monster that eats spacecraft that are on their way to Mars. Galactic Ghoul, is that it? And so it's just like spacecraft for spacecraft just crashed on Mars, and they weren't able to figure it out. Now NASA had a really high success rate, but the Russians just lost spacecraft after spacecraft. It's only recently the Chinese were able to land on Mars, and NASA has the Galactic Ghoul. I did get it. Okay. And then NASA's had a pretty good success rate, but a lot of other countries have failed. So the problem with the moon is that it is very small, that you've got the gravity of Earth that is interfering with your attempts to land on the moon. There's no atmosphere that slows down your spacecraft. So you got to be able to do all of your landing purely through propulsion. Have you ever played, those lunar lander games, right? You've got to be able to fire your thrusters at the right direction at the right time. And they all seem to run into some kind of problem. Their thruster fails. They misunderstand the distance to the ground as they're trying to do some kind of automated landing. And a lot of it is just like new companies are attempting to land on the moon for the first time. You've got Israel with the Beresheet lander. You had India with their first Chandrayaan lander. You've got the Japanese private company. You've got an American private company. And then you can compare that and contrast that to, say, the Chinese that have built up a track record of landing spacecraft on the moon. They're up to they've done Chang'e 5 So they've definitely built up this experience in landing on the moon, and will continue with their future missions. So I think when we see all of these groups that have crashed on the moon take their second chances at it, I think we're going to see a lot more success. While in Domini, suggestion for all space organizations: make vessels land on any side with legs sticking out all around and rotate science equipment after landing to avoid the fate of Japan's nose-diving moonlander. Yeah. Nobody expected that one of their thrusters was going to fall off, which caused the thing to land on its nose upside down. But space is tough. Derek S., what do you think of CERN's proposal to build an even larger version of the Large Hadron Collider to search for dark matter? Can you find dark matter? And if you do, how will you recognize it? I don't have an opinion. I know people like Sabine Hossenfelder have a strong opinion, but she's a particle physicist. So of course she's going to have opinion, and other people have different opinions. One of the problems with the Large Hadron Collider is that it was just too successful. They built this enormous facility. Its job was to find the Higgs particle, and it did. Early, quickly, immediately, it found the Higgs particle. And then, boom, job done. Now the question is, what else can we do? What other cracks in the particle, in the standard model of particles, can we open up to try and find other hints and mysteries? And nature is just not revealing its secrets. They keep trying higher and higher energies, and they keep not finding anything. And then they've been testing other theories and other particles and so on. But, there are still these fundamental questions about how you can resolve, how do you integrate quantum mechanics with gravity? And there is one line of physics that just says, okay, we're out of ideas. We're not out of ideas. We have provisional theories that might be able to be explained, but we're going to need particle accelerators of higher energies. And so and I know Sabina's argument is come up with better theories first, come up with very specific things that you're looking for, and then build experiments that might not look anything like a particle accelerator to find out if those particles exist. And while something like a much larger version of the Large Hadron Collider is an all-purpose tool, it is a Hubble Space Telescope of particle physics. It is a James Webb of particle, although James Webb is more specialized than Hubble. So it is a LUVOIR of particle physics. And I think, there is an argument to be made that just more energy, more boom. Interesting things will happen when you knock together particles at the highest possible energies that humanity has ever created. But the question is, how do you want to spend your money? Like it's if you had an infinite amount of money, then it makes sense to do whatever you want. But we never have an infinite amount of money. We have finite resources. And so if you have a finite amount of money to spend on certain experiments to probe certain parts of nature, do you go with the big all-purpose tool that has no specific objective, or do you go with a collection of smaller experiments to test out more interesting and more radical ideas? And I think now that the Large Hadron Collider has been completed, I think there are improvements and tweaks that can be made. When you think about what happened with LIGO, they were able to make, every couple of years, they shut down LIGO, they improve a whole bunch of the instruments and experiments and power levels and all that, and then it comes back online, and it's a much better instrument than it was before. And so my guess is that there are several more years of upgrades and improvements that can be made with the Large Hadron Collider. And I think there are really creative ideas to search for things like dark matter, things like that require some budget, that could use some attention. And I think you'll see this swing back and forth where, okay, now we're just building the most powerful particle accelerator humanity's ever seen. We're going to crash things together at the highest energy, and we're just going to look through the rubble and see what we find. And then there is, okay, we've got these 100 great ideas for where dark matter or other particles could be hiding, or other ways to test gaps in our current understanding. Let's build these smaller experiments that do one job. And then when they're done, we shut it down, and then we move on to the next thing. You don't get general answers. You get very specific answers, but maybe those specific answers can inform the big super version. And there's no easy answer to this ever. You're always going to have this balance back and forth. And I don't envy the people behind the funding agencies that have to deal with this. All right. Richard Harris, how come we've never been past low Earth orbit? So this is your question. Why have we never been past low Earth orbit? We've absolutely been past low Earth orbit. The Apollo missions went to the moon. We've got tons and tons of spacecraft that have gone well beyond Earth orbit. Like when the James Webb Space Telescope was flying out to the L2 Lagrange point, amateur astronomers were tracking its movement in the sky. Independent amateur astronomers who can double check each other's work. When the DART spacecraft crashed into asteroid Dimorphos, independent amateur astronomers were able to watch and see as they saw the flash and the cloud of debris after the satellite crashed into its asteroid target. People regularly bounce signals off the moon. So we know that there are retroreflectors on the surface of the moon. There's just so much evidence. We've got the Artemis 1 mission that just went to the moon. People tracked it. And you don't just have the people who are launching the spacecraft, NASA and so on. You have the enemies of the people who launched it that are also tracking it. You know, like the Russians, the Chinese are watching what everybody else is doing in space. And if anybody was up to any kind of shenanigans, then the easiest way to prove that you are, that your enemy or your rival is not able to accomplish what they do is, you can just prove it. You'd be like, haha, they said they went to the moon, but they didn't because we saw, and here's the proof that in fact they didn't. And everyone would go like, oh yeah, wow, they're all liars. But no, they celebrated the accomplishment by their rivals. They congratulated the Americans for going to the moon. And we're about to send a lot more humans into deep space. The Artemis 2 mission, which is due for 2025, is going to have 4 astronauts on board, including a Canadian. And they're going to fly out around the moon. They're going to do a few orbits around the moon, and they're going to drop back down to Earth. And then in probably 2026, but let's be honest, it's going to be more like 2027, we're going to see humans go to the surface of the moon. And if it's not the Artemis 3 people, then the Chinese are going to do it in 2029. The Chinese are going to set foot on the moon, and that will be the beginning of a series of missions. And within a decade from now, we will have some kind of long-term presence on the moon. You're going to have either a research station from NASA and the European Space Agency, or you're going to have a research station from the Chinese, or both, or the Chinese and the Russians, or maybe we're going to have one international research station. That would be my preference. And we'll be able to look up into the sky as we watch the International Space Station float overhead for like one more year before it gets deorbited. And you'll go like, there's 10 people on the station right now. And then there's that private space station over there with a whole bunch of rich billionaires enjoying zero gravity. And then when you look at the moon, you're like, there's people there right now. And there will be a permanent presence of humans on the moon. He's a Canadian. Will he land on the moon and apologize? He's not going to land on the moon. He's just going to go into orbit around the moon. We would never. I'm so sorry. I'm so sorry. Awesomepotamus. About gravity. We know about gravitational lenses. Are there other gravitational optical effects? For example, gravitational mirrors. Not really. I mean, everything is about lensing with gravity. But you can sort of think about what happens to light as it is lensed around a black hole. Light can do a 180-degree flip. So you could have light go towards the black hole, go all the way around the black hole, and then come back out the other side. And so that's like a mirror. You could look at yourself in a black hole in the mirror. Vistotuti, have you heard any updates on the enormous volcanoes on Mars and Venus? Do planets without plate tectonics catastrophically spew their guts out? I mean, no updates since the last time we talked about it. I did an interview with Paul Byrne like maybe 6 months ago, and we talked about their discovery of potentially active volcanoes on Venus. We know that there is still some level of volcanism on Mars, but Mars is almost dead. Christopher Peter Van Der Essen. Can Stirling engines be used for power in space and on the moon? Can giant mirrors be used for mining the moon and asteroids? So let's go with the Stirling engines. So yeah, Stirling engines have a purpose in space. And I don't know exactly how Stirling engines work. They're like a heat pump. Like you move heat from one chamber to another, and you're able to use that to drive mechanical pistons that allow you to extract electricity. And there's been a proposal to put a Stirling engine on a rover on Mars. And so while the inside is cold and the outside is hot, and as the heat transfers from the outside of the rover into the interior of the rover, you use that heat differential for electricity. And in fact, the Chinese recently tested out a Stirling engine on one of their satellites. And so this is a possible, like right now, most of the deep space spacecraft use a radioisotope thermoelectric generator, a decaying chunk of plutonium. And then they hook up a thermocouple, which sort of turns heat into electricity. And what the Chinese are testing out is, can you use a Stirling engine? You would attach one side of the Stirling engine to the plutonium, which is very hot. The other side is cold. And then that heat differential is something that you can use electricity mechanically. And their tests worked out great. And so we could see future spacecraft, instead of using this thermocouple, maybe it's going to be more efficient to extract electricity using a Stirling engine, like a heat pump. KGS, do you think the position of the solar system in the Milky Way affects the disruption of Kuiper Belt objects? Probably not, but there's like one theory that when you think about the galaxy and how like all of the stars are rotating around, they're orbiting around the center of the galaxy. But in fact, they also oscillate up and down, kind of like waves as they go up and down in the galaxy. And so the thought is that maybe as the sun goes up above the plane of the galaxy, then it's less protected from the cosmic radiation by the mutual magnetic field of all of the stars in the Milky Way. And so like maybe like increased light pressure or cosmic ray pressure could move Kuiper Belt objects around, but no, I can't really sort of imagine how it would be as stars or rogue planets make close flybys of the solar system and they disrupt objects in the Oort cloud or the Kuiper Belt, that would cause Kuiper Belt objects to fall down into the inner solar system and cause impacts on Earth. Bravo 01, can particle accelerators create auroras? I don't know. I mean, I know that you could create artificial auroras like with the HARPS experiment in Alaska. Paul Wilson, what's your favorite galaxy? The Milky Way. But like, what's my favorite one to look through? I think I like the Sombrero. Like if I look through a telescope at a galaxy, the Sombrero galaxy is pretty neat. Electric Master, is space dementia real? Maybe. One of the possibilities is that increased radiation has an effect on the brain that can cause some level of dementia. This is something that people are still studying. What are the effects of space, the long-term effects of spaceflight on the human body? Like we know that the astronauts have increased risk of cardiovascular issues. Like we know that being in space, especially the Apollo astronauts, right? That is, as soon as you leave the atmosphere of the Earth, as soon as you leave the protective magnetosphere of the Earth, then you're getting an increased radiation load, but also like what effect is this having sort of at a cellular level on your body as your body adapts to being in zero gravity, but also being in this higher radiation environment. And there is like a real effect. And so one of the thoughts is that this can have, if you're going to go to Mars, there can be an effect on your brain. And nobody has just done long enough missions. Like the most any human has ever been away from the protective magnetosphere of Earth is like a week. Like we don't know what happens when a human is away from Earth for a month or 3 months or 6 months. And that's one of the valuable things about the Lunar Gateway is that when astronauts go to the Gateway, they can start to do all of those experiments they did in low Earth orbit in the International Space Station, but now do those at the Gateway and say, okay, fine. Like what happens to a person when they have been, in deep space for a month, and compare that to what happened to an astronaut in low Earth orbit. And you'll start to get a sense of just how much more dangerous deep space is than low Earth orbit. But spoiler alert, more dangerous. Like there's no protection. Paula Wilkins, is it amazing that water stops radiation? Just curious, are the newer spacesuits built with water to protect? Not that I know of. I mean, yeah, I can imagine that spacesuits would put like a layer of water around on the inside of the spacesuit, but like that's a big engineering challenge. It's better to just have a place where you keep the water inside your spacesuit. And like for the amount of water that you need to be able to protect yourself from radiation, like it's a meter of water. So yes, a thin layer of water would help, but like not very much. You really need that meter of water. So you can imagine being in some kind of rolling water ball on the surface of the moon that has a meter thick of water. I'm designing a future moon rover here. That would work. I love that idea. Like think about those like balls that people like go down steep mountains, inflatable balls, and there's water inside, and it's like safe but also terrifying. Yeah, imagine you did that, just rolled around on the surface of the moon in a big water ball, and they'd be easy to like get the regolith off, easy to wash off. Yeah, I think I've cracked it. Where's my NIAC grant, NASA? Leonard N. Fraser, do you think it's inevitable that humans are going to live in space permanently, like the show The Expanse? Do you think there will inevitably be a distinct species because of all the adaptations? So I just did an interview with Zach and Kelly Wienersmith about whether or not there will ever be a city on Mars and long-term habitation. And, a lot of people like listen to that interview and they're like, oh man, what a bunch of grumps. They don't think that, they have no imagination. They can't imagine a time. So let me just like state this unequivocally. As he says, coughing, needing a drink of water, increasing the suspense. Okay, ready for this? Unless something catastrophic happens to human beings, I think that eventually we will inhabit every nook and cranny and corner of the solar system. Every planet, every asteroid, everywhere that is worth living in giant orbital colonies, all of that. It's just not going to happen soon. It's going to happen when the technology is ready, when our infrastructure is ready, when we have trivialized living in space. And the thing that I'm trying to get across is that I think that people, as they're so excited about like we're gonna move to Mars, Elon Musk is planning to build a city on Mars with 1 million people, that it's going to happen soon, that it's going to happen in 8 years, that it's going to happen in 10 years or 20 years, and they're going to terraform it, and it's going to be great. And we're just like, we're not at that part of the technology ramp up, of the exponential progress. We're in this is all really hard, and there are 1 million little problems that need to be worked out, and there's no value to working out any of those problems, and so no money's going to be spent to work on any of those problems, and life on Mars is not sustainable until those problems have been solved. But as our technology increases, as we build new methods of propulsion, more compact forms of energy generation, better communication systems, micro fabrication systems that allow you to create things, 3D print things out of, sand that you find on the ground, then we become more capable of living in other places, more extreme environments where we trivialize them. Like if you could have a home on Antarctica that would only take you 5 minutes to go from some other place on Earth to your home in Antarctica, that it was warm, that had a well-stocked fridge, and you had a beautiful view out to the ocean. Would you like that home, please? Yes, you would, right? That sounds great. But if you needed your home in Antarctica to require a trip from Antarctica on a $10,000 boat trip to get you to your home in Antarctica, that there are no local resources, so you have to bring everything, you have to carry your fuel in diesel cans, all of the food is going to be rations, you show up on your at your home in Antarctica, and if anything goes wrong, you have to wait 6 months to be rescued, that the temperature outside drops down to -80. It's rough. And so like, would you like to live there? And you're like, well, maybe not. Right. So we live where we live because that's what we can afford. You make these decisions every day in your life. Where you live is what you can afford. As you make more money, you can live in a nicer home, and you can live in a better part of the world. You can live in, nicer scenery and so on. And so there's nothing that is going to make Mars magically a better place to live. It is a terrible place to live by every measurement that we could possibly imagine. And so technologically, we are just not ready to do it. And because there's no money to be made, it's not like you can go and trade with the locals, or you can extract resources from Mars and make more money than if you just pull them out of the ground. There's no money to be made, and the place is awful. And so we are just not ready to live there. And I think that the worry that I have is that people are going to they're going to get a bad feeling about this whole space exploration thing, that they're going to lose sight. Like they're going to be like, Elon Musk promised me that we were going to live on Mars, that the first spacecraft was going to fly to Mars in 2024, and then we would be starting to build a city on Mars, and it didn't happen within 5 years, and it didn't happen within 10 years, and it didn't happen within 20 years. Well, you go talk to a person who watched humans land on the moon, who watched Neil Armstrong set foot on the moon almost 60 years ago, right? Did you think that you were going to have to wait this long? And they'd be like, no way. I thought we thought this was the beginning of the new space age. Well, we weren't ready. We weren't ready then. We're ready now. We are ready now to set up a permanent science base on the moon. It's a fraction of the price. It's like 1/10 the price to send astronauts to the moon today than what it was to do it back in the Apollo era. And so now it makes sense to go back to the moon. We've got miniaturization. We've got reusable rockets. We've got new technology. We've got computers, new methods of communication. So I am a gigantic fan of whatever the future of humanity, the positive future of humanity is, the one that has us on living across the solar system. But I don't want us to do it before we're ready, where it doesn't make sense, because when we invest in things that don't make sense, then we lose our money, then we lose lives. And instead, let's develop all of the underlying technology. Let's expand our capability. Let's learn to live in closed loop environments. Let's explore our space. Let's send humans back to the surface of the moon. Let's send the first explorers to Mars. Let's go to asteroids. Let's explore the solar system. Let's understand what the shortcomings are. Let's improve those shortcomings. And the only reason we're doing it is because we explore, because it's worth doing, because space is what's next. And as soon as you justify, you say, well, we're going to go because we're going to make a lot of money from asteroid mining. And then if you don't make money from asteroid mining, then you don't go. Well, did you forget that space was awesome? Space is awesome. Don't forget to go to space because it's awesome. And so, there have been asteroid mining companies, startups. Like when I started Universe Today, 25 years, people have been trying to do asteroid startups. There have probably been 10 of asteroid. We're going to start a company, and then we're going to learn to mine asteroids, and we're going to make a profit, and we're going to return metals to Earth, or we're going to provide volatiles to, provide water to satellites. They all fail. because it's too early. And they're just like, if you want to lose a bunch of money, you start an asteroid mining company. But so don't depend on, oh, we can make a profit from this as the reason to do this. So I think that, again, as long as we survive, as long as we avoid existential threats, then the future of humanity is going to be amazing. Because you've just got exponential growth that just keeps making problems go away, that keeps our standard of living growing. All of the, bad things go away. Hopefully, when we think about things like climate change, all that, hopefully we'll get our hands around each one of these problems and we'll move towards that future. We will stumble towards a more interesting, better future. And I absolutely genuinely believe that's coming. So I am the greatest enthusiastic fan of space, but I think that you need to have really good reasons why you're going to do it. And I think that that's my justification, because it's awesome. So do I think it's inevitable? Yes. Do I think it's going to happen in my lifetime? No. Do I think it's going to happen in your lifetime? I don't know how old you are, but no. McBandit Hope. How visually different would a habitable planet around different colored stars? Would colors work, for example? Yeah. So if you were on a planet around a red dwarf star, then everything would be red, because the star is putting out red light. It would be kind of dim and red, but it would be warm as long as you're in the habitable zone. There's been experiments that have been done to find out, like, can plants grow under red dwarf star light? And some plants can and some plants can't. So, but yeah, it would be. And if you were around a blue star, then things would be bluer. And like, we have that. I mean, I could change the lights in this room so they are more blue or they are more red. Jason Rivard, is there any functional difference between a von Neumann probe and space life? Aren't they just the same thing? Well, I mean, it depends on your definition of. That's kind of like saying, is there any functional difference between a computer and a human brain? I mean, aren't they just computers? And like, there are functional differences. One is made of silicon and one is made of meat. One is fairly resilient and can be mass produced using chip fabs and sand, and the other, is produced in other ways, and requires a lot of time, and they're very fragile inside your skull. So, the idea of von Neumann probe is that it is a robot in space, some kind of robotic factory that can make more copies of itself. And like, if you haven't read the We Are Legion, I Am Bob series, they're so good, the Bobiverse books, and that is a von Neumann probe, where he finds asteroids, tears them apart, uses them to make more copies of himself, and moves to other star systems. And like, is that what life does? Sure. Yeah. Life exists in an environment, and it finds local minerals and ingredients and food, and then it uses energy and it adds it to its body and makes more of itself. And so sure. Yeah. The trick is that, you're not going to get a hippopotamus flying out to space and going from star to star and crunching up asteroids. Like, so it's purely an expectation of what the thing is going to be, that is going to be a robot factory that is capable of taking in energy from the star, raw ingredients from the solar system, and make more copies of itself. And I think, like, when you think about like planet Earth, there's a limited amount of resources. If you think about, the process of evolution on Earth, we are at maximum usage of planet Earth. That every nook and cranny of Earth has been exploited by life. That, when you go into a forest, a natural forest, that every photon that is coming from the sun is being intercepted by some plant. Every molecule of carbon of whatever, carbon that falls to the ground or nitrogen that falls to the forest floors, then utilized by some other plant or some mushroom or whatever, that without human beings, Earth sort of reaches its maximum usage of all of the resources that fall on planet Earth. But Earth life can't get off Earth. So we can extract and use every single piece of energy and matter that falls on Earth. But when you think about von Neumann probes, they can use every piece of matter and energy that is available throughout the cosmos. And that's more. And so it's a distinction of scale. All right, let's see where we're at. 10 more minutes. Emiliano Lineri. Do you think there's a point where there's going to be so much space junk on Earth orbit that's not going to be possible to launch spaceships anymore? No, I don't think we're ever going to reach a point that we can no longer launch spacecraft. Even with tons of more space junk, it's just going to be an increased risk. So right now, let's say that there's a 1 in 1,000 year chance that your satellite is going to be impacted by a piece of space debris. And as we get more and more debris and the debris breaks up, maybe there's a 1 in 100 year chance, and maybe there's a 1 in 10 year chance, and maybe there's a 1 every year chance. So we are sort of caught, it's like an increased friction, and we'll never get to this point where space debris turns into this impenetrable shield of sandpaper grinding metal that any spacecraft that tries to leave just goes through this buzz saw and is just fragmented. We won't hit that, but we will hit a part where spacecraft go through and you have to be very careful and you have to make course corrections all the time, and it's a pain in the butt to do that. And so it is it's an increased expense. Paul Cowell, what role will AI play in future deep space exploration? Huge role. Already we have AI that's playing a role in navigation for spacecraft, for landing, like the Perseverance rover used artificial intelligence to pick its landing site when it arrived on Mars. And the farther away you are from Earth, the more time you need to be able to communicate to and from your spacecraft. And so you just can't give it detailed instructions. You send a spacecraft to Pluto, it's going to need to use artificial intelligence to decide where to take pictures, how to orient its cameras, shutter settings, all of that kind of stuff. So no, I think the more artificial intelligence we can use for this process, the better deep space exploration is going to become. Ernest Petra, what do you think about the Drake equation? Do you think it has its validity? I don't think the Drake equation is very useful. So, the Drake equation is this classic 6 number calculation. I forget the numbers. 1 is the number of planets orbiting stars in the habitable zone in the Milky Way, and 1 is the number of civilizations that don't kill themselves with nuclear war, whatever, right? And that all the time people can come up with other things, like what if it doesn't have a large moon, and what if it doesn't have a large planet that may be protecting it or may be threatening it. And at the very heart of it is we don't know how often life forms on other worlds. Right now, we only have one example of life in the entire universe, this one planet that we're on. We don't know, which is really weird. When you really think about that, right? We're at a time in history when we didn't know the answer to this question, are we alone in the universe? And 1,000 years from now, our descendants will have an answer to that question. Now, it'll either be, we found life in a bunch of places, life's everywhere, there's a galactic federation, we're part of it, nanu, or we've searched in larger parts of the universe, and we, with 99.999% certainty, say that there's no life in the universe. And so We don't know. Like, and I know your gut, your instinct tells you that that it can't be. We can't be alone. The chances have got to be, and then you come up with a number that you just pull out of thin air, right? It's got to be 1 in 1,000,000. It's got to be 1 in 1,000,000,000, but we don't know. It could be 1 in 2, and it could be 1 in quintillion. And if it's 1 in quintillion, then there aren't any within tens of millions of light years of us. And if it's 1 times 10 to the power of, here he does scientific notation in his head, 15 plus 12-ish, 27. So, a 1 followed by 27 zeros, then we're the only place in the entire observable universe that life formed. And we just don't know. We don't know what that number is. And so I think the Drake equation is neat, and it sort of makes you think about the possible, but it is not a useful equation, unfortunately. Sorry, I'm just looking for people who haven't had a question answered yet. What are we at? One more. I think. Paul Wilson, can Webb and Hubble be used together to create an effectively larger telescope like we do with multiple telescopes on Earth? So they can act like an interferometer, like where they combine the light and use the separation, but Hubble and Webb work together all the time, where you take an image from the Hubble Space Telescope, which is in optical, and then you also take an image of that same place in infrared using Webb, and then you compare and contrast the things you're looking at. And then people also do that with Chandra. So they look in X-rays, and then you say, well, here's all the X-ray sources, and here's all the optical sources, and here's all the infrared sources. And that's what they do. All right, maybe I'll do one more. Tony Kona, what's the deal with getting the rest of the info on the exoplanets in the TRAPPIST-1 system? Only gotten B and C and need the others. That is a great question. What is the deal with that? Like if you've been following a bunch of the interviews that I've done, I've asked that question directly to researchers who know the answer to that question. So I think the answer, and I don't have like an official statement from anybody, right? But I think the answer is that red dwarf planets suck, and that they're looking for an atmosphere and they're not finding one. That would explain it. But also they found an atmosphere and it's filled with biosignatures and they want to confirm it so they don't look like idiots, would also be a perfectly reasonable explanation. So we just got to be patient. We've just got to wait. And just wait for this answer to come out. I'm sorry, I know. Edward Glubin, what is your background, Fraser? I'm new to the channel. I've been loving all the content. So my background is actually in computer science, is my degree. I've been into space and astronomy since I was a child. I went and saw meteor showers. I bought my first telescope when I was like a teenager, 14 years old. When people were partying, I was organizing star parties. Such a nerd. I was in the journalism program in my high school, and I reported on space and astronomy news for my high school newspaper. And then I went to the University of British Columbia for engineering, and then decided that wasn't for me, and went into computer science. I worked for computer science companies, worked for web development agencies, software companies in Vancouver for a few years, like from 1995 to 2000. And at the same time, I was like, I had all these crazy ideas about how to run a website, and nobody would listen to me. And so I was like, well, I'm just going to pick one of my hobbies and work on that. And the one that I picked was space, because I was really into space, and I was reading The Case for Mars and Pale Blue Dot. And I thought, well, I'm going to run a website about space where I'm going to report on news that's happening in space. And while I do that, I'm going to learn about space. And within a couple of months, I was like, you know what? This is all I want to do for the rest of my life. I've loved this so much. And that was 25 years ago was when I started Universe Today. Like we're about a month and a half away from my 25th anniversary of running Universe Today. So I don't have a degree in any of this stuff, right? My degree, again, my degree is in computer science. So, I have the physics required, the math required, all of that. So I have a year of engineering, physics and mechanics and calculus and linear algebra and chemistry and all of that. And then I have all of the computer science stuff, algorithms, more linear algebra. But I don't have the higher level physics. I don't have the more complicated calculus, multivariable calculus. I don't have specifics in astrophysics and all that kind of stuff. So everything I know is me either grilling Dr. Pamela Gay every week on Astronomy Cast, where she gives me a personal education in all things space, or all of the interviews that I do, or all of the research that I do, or all of the interviews. And so, I think the more that I learn and the better I get at this job, the more I know my role and I know my place. And that's why I am ever so loath to speculate and about the kinds of things that I don't have an opinion on. I shouldn't have an opinion on because I'm an amateur, right? I am an enthusiast and I am a journalist, but I am not an actual scientist. And so I'd rather ask my questions to the scientists. So that's my background, is 25 years of in the trenches space journalism. All right. I think it was a fun last question. Thank you, everybody, for hanging out. Fenris Walker, I don't understand. Where are the questions you are answering? You just had your question answered. Right. Thank you, everyone, for hanging out this week. This was super fun. I always have such a good time. I can make these longer. I have such a good time. And there's a lot of questions. So what's coming up? Interview with David Kipping. Wrap that up on Friday, and it's so good. Like an hour and a half. We just yacked forever. So I think you'll really enjoy that episode, that interview. I've got a bunch more really interesting interviews coming up. I did an interview with a researcher who is trying to create a James Webb version of the Hubble Deep Field, which I know you're all hoping to see someday. So we talk about that. That's another interview. I got an interview with Dr. Paul Sutter coming up, and many more. I've got an interview with the principal investigator of LISA coming up. All right. So like the Gravitational Wave Observatory, I'm going to be talking to the mind behind that. So stay tuned. Lots of good stuff. A huge thank you to John Suffield and Zapfan. Please give it up for them for sticking around and helping me organize this thing. I couldn't do this show as efficiently as I do without their help. So thanks, guys. I really appreciate it. All right. I'm going to go to bed now or eat some food. I don't know. Thanks, everybody, and we'll see you next week.